A very good morning, respected sir and fellow mathematicians of the day. Today, I, Adishri Shaiju, your own classmate, will be presenting to you on the topic sets, the first chapter of grade 11 mathematics and the mathematics field set theory. So first of all, what is this whole set theory as such? In the world of mathematics, there are many different theories. Set theory is just one of them. However, if I start going too deep into this theory, it will take forever to explain. The world of mathematics is never finite. It stretches on and on. That is why we will be focusing on a certain part of the set theory. A certain theory which is very simple to understand but governs the true and fundamental meaning of mathematics. Now, let's find out about the certain mathematician who is responsible for the whole set theory. It is none other than George Cantor himself. The German mathematician who lived from 1845 to 1918 was a very talented schoolboy who went on to become a mathematician, something which he felt had his talent. One day, Mr. Cantor was working on the trigonometric series of the form a1 sin x plus a2 sin 2x plus a3 sin 3x when he came across a pattern. But what he wanted was to arrange them in a certain set of numbers. That is where sets came into play. Cantor found this very interesting and further worked on this, and that is how we have the modern set theory today in mathematics. How did Cantor perceive sets? Well, behind me you can see a few shapes. These shapes can be obviously called polygons. How do we define a polygon? A shape with a definite side and have an angle, unlike a circle which has no side. Therefore, we can see that the elements behind me, or the shapes, possess a common property, and hence I call them the polygon, and hence they are under the set. This is what Cantor had perceived in his time and what we use today in mathematics. In the simple definition, set is basically a well-defined collection of objects. You could also say elements or members. These all are synonymous terms. The sets, which are usually enclosed in the curly brackets, are always denoted by capital letter A, B, C, X, Y, Z, you name it, any letter. However, do keep in mind that the elements, that is the numbers enclosed within the curly brackets, are in small letters such as small a, small b, c, d, e, f, etc. That is the basic fundamental meaning behind sets. In mathematics, we use various types of numbers such as natural numbers, integers, rational numbers, even real numbers, as well as the newly learned complex numbers. But to keep the idea of sets more clear and simple for all of you, I'll be only covering till real numbers for today. Moving forward, as you can see, there are many commonly used sets in mathematics, mainly based on these numbers, such as that of n, z, q, r, and you can see some of them have like q positive, z positive and r positive. Wait, what are those? Let me explain you in brief. N stands for the set of all natural numbers. When it comes to z, the set of all integers. Q for the set of all rational numbers, which can be expressed in the form p by q, where q is not equal to 0. And r stands for all the set of real numbers. But this plus sign above the z, q and r stands for only the positive part. I repeat, just the positive elements from the set. That is, if you consider z plus, it stands for all the set of positive integers. When it comes to q, positive rational numbers. Comes to r, positive real numbers. Once again, these only represent the positive values. Moving forward, mathematicians are very concerned about arrangement of different elements. I mean, when it comes to any question, they are really concerned about the matter. That is why they mainly divide the idea of sets into two major forms. One, the rooster form or listing form, and the second is a set builder. Let's move into them one by one. Rooster form. What exactly is it? Rooster form stands for those elements which are expressed in a list enclosed by the curly brackets. Let's say an example of all the vowels in the English alphabet. They are enclosed in the curly brackets A, E, I, U. These are all the English vowels. This basically can be of any order too. There is no hard and fast rule that they have to be arranged in certain orders. Any order is acceptable. But do keep in mind, in a set, we usually do not repeat an element. In the case of school, SCHOOL. But while representing the set, we say SCHOL, school. Yeah, I know that, but we are concerned about the mathematics, not the English here. So we only make sure the elements don't quite repeat. But when it comes to set builder, we are building a set, and that means the set must have a common property. What do we notice in these letters A, E, I, O and U? That is, these are vowels of the English alphabet. Hence, when we are representing in a set, for example, let the set be V. V is equal to, in curly brackets, X colon, X is the vowel of the English alphabet. What do these curly brackets and colons stand for? Are those English punctuations? No sir, these are actually certain mathematical terms. That is, the curly brackets stand for the set of all, that is over here X, and the colon stands for such that. Now if I had to read it out mathematically, it would be V is equal to the set of all X such that X is the vowel of the English alphabet. Moving on to the different types of sets. The first one is the null set, or you can call it the void set, or even the empty set. In this set, there are no elements. Literally, the number of elements in this set is 0. Hence, we can represent it by two ways, either by the Greek letter phi or otherwise by empty curly brackets. That's right. An example you ask? Well, the set of all X, such that X is a student who studies in grade 10 and 11 in the school. Wait a minute, I don't know of any student who can do that, at least as of now. So to this present moment, we would consider the set to have 0 elements. That is the idea of the null or the void set. Moving forward, yes, infinity. Infinity has always been a surprise to mankind. We can't call infinity a number, it's more like a theory. And this theory applies to sets as well. That is why we have two subdivisions of sets as a finite set and the infinite set. In the case of finite sets, they are those sets wherein the elements are actually finite. For example, the set of all, let's say, numbers from 1 to 100, 1, 2, 3, 4, etc. to 100. These are finite, we can count them. What if I say the set of all natural numbers? We will never be able to finish counting, even towards the end of the time. That is why we call that type of set an infinite set. Now we'll be talking about two other categories, the equal sets and the equivalent sets. Equal sets are those sets wherein the value of the elements are the same. Let there be set A and set B, which each are having 5, 10, 15 and 20 as the elements. Such sets will be equal, as you can see in the example over given. Moving forward about equivalent sets. These are sets wherein the number of elements are the same, need not be the value of the elements. That is, the cardinality as described in mathematics is the exact same, like given in the example wherein set C and set D both are having 4 elements each. Thus, they are called as equivalent sets. Now moving forward to subsets. Let's split the word sub and sets. Sub means a part of. Hence, subsets are basically a part of a bigger set, which later will be called the universal set. The definition is very simple. A set A is a subset of set B in case all the elements of set A also belong to set B. In the given example, as we can notice, the elements of set A are also found in set B, yet set B is a larger set. However, if you compare them, the elements of A are always in B. That is why we call A as a subset of B, but never call B a subset of A. That makes absolutely no sense. So keep that in mind. Now we are moving on to a very important category, both in mathematics as well as in set theory. That is the idea of intervals. In mathematics, each of the brackets have a lot of importance. Yeah, regarding BODMAS, that's another story. But in this side of mathematics of set theory, each bracket, like I said, has a whole new meaning. The curly brackets, like I already told you, are basically representing sets. But the square brackets and the normal brackets are a whole new phase of mathematics. Intervals are basically the subsets of real numbers. Remember the term subsets? Keep that in mind because there will be a lot of discussion based on it. We can represent real numbers in various ways. Intervals are just one form. In the case of intervals, like in the between numbers 1 and 2, there are infinite number of real numbers. We cannot write each one of them down, hence we use intervals as a primary source of information. When we say that it's both enclosed in the normal parenthesis or the circular bracket and then write AB, that is a part of the number line where A and B are excluded and all the elements inside it are confirmed. When it comes to a square bracket on A and a normal bracket, that is normal curve or parenthesis on B, it refers to those elements where A is included with the middle numbers but B is excluded. The opposite, that is where there's a parenthesis on A but a closed bracket at B, refers to the fact that B is included in the comparison. That is, A is less than X is less than or equal to B, referring to slack inequalities. Like I said earlier, the square bracket also has another meaning. That is, in the previous two examples I just mentioned to you about closed bracket A, comma B with a parenthesis and A with a parenthesis and B with a closed bracket, these have a lot of difference. But what if A and B both have closed brackets? That is the square brackets. In such a case, we would usually call it a closed interval, wherein all the real numbers between A and B are included as well as A and B, including the two numbers. Moving forward, if you further think about it, these intervals can also represent the whole set of real numbers. We know that real numbers range from minus infinity to plus infinity. No more, no less. Therefore, like I said in the beginning, infinity is not a number but a theory. Hence, we will never be able to include infinity. Thus, we usually put both open brackets, that is, open bracket minus infinity, comma, infinity with an open bracket. This denotes to the actual meaning of real numbers represented as R. The next one is a very interesting topic, power sets. Well, not exactly like that, but we get the point. Power sets are the subsets in a set itself. Let's take a set in the curly brackets 1, 2 and 3. They have a number of subsets. What if we make a set including all the subsets? That is called the power set of this set. Let's say the set name is A. The power set of A will be P of A in brackets. They will be null set because nothing is found in everything. It's a very famous theory in mathematics. Nothing is in everything. Hence, the null set which I told you earlier will also be a subset. Therefore, the different subsets would be the null set 1, 2, 3, each of them respectively in their curly brackets, then 1, 2, 1, 3 and 2, 3 along with 1, 2, 3 because each set can also be its own subset. This is the basic fundamental meaning of the power set. There's also one more idea. How would you find for a very huge set, like let's say the set B is equal to 1, 2, 3, 4, 5. Let's say a set A has m elements. The number of subsets in P of A would be 2 raised to m, a fundamental property which you must always store in your brain. Next is the universal set. At last, I've been talking so much about this universal set and you may be wondering, what is a universal set? That is what I will explain to you now. Universal set is the main and basic set from which all the other subsets are derived based on the context. Based on the context, let's take two examples. One of the human population studies. When we consider such a vast subject, we need a main base from where we can take the topic. Therefore, scientists usually consider the whole human population as a universal set, wherein the age of men and the population of women are taken as subsets. Similarly, mathematicians take real numbers or even sometimes complex numbers as the main and universal set from which they derive the other subsets. This is the basic understanding and fundamental meaning as meant by George Cantor when he talked about universal sets for the very first time. Well, we move on to a very interesting topic known as the Venn diagrams. Yes, the English logician and mathematician John Venn is the man who came up with this brilliant idea. Two circles, merge them together, you get a common part That's called the Venn diagram. We'll be using Venn diagram to illustrate the main set operations. Just like we have addition, subtraction, multiplication and division as arithmetic operations, we also have set operations, that is called the union of sets, the intersection of sets, the difference of sets, and at last but not least, complement of sets. Now we'll be moving on to the very first and foremost operation known as the union of sets. Let there be two sets A and B as per this Venn diagram. Then when we say A union B with a capital U, well, almost similar to a capital U, it will be written as A union B, which is equal to, and we must write those elements which belong to either A or B, or belong to both in fact. In simplest words, it's similar to or analogous to the addition idea which we use in arithmetic. Moving on to the intersection, almost the exact opposite of that of union. In the case of intersection, once again, let there be two sets, A and B. When we say A intersection B, it is basically written as A intersection in the similar way or the similar fashion of an upside U and then a B. When we say equal to, this operation requests the mathematician to write those elements which are common to both A and B. In the case of Venn diagram, don't you notice that common intersection of area between both the Venn diagrams of the circles? Elements included in that category must be included in A intersection B. Therefore, we could also mention that intersection is almost the exact opposite, and also there are keywords to remember. That is, for the A union, we would say either or. In the case of intersection, we would usually use the word and. Now we'll be moving on to the difference of the two sets. Let there be two sets, once again the old and boring A and B. Now these two sets, A minus B and B minus A, stand for the difference of the sets. What do they mean? Let's take A minus B. A minus B equals to the set of all x such that x belongs to A but does not belong to B. In the case of B minus A, it means the set of all x such that x belongs to B but does not belong to A. Once again, each of the respective elements or the sets for example A minus B, in that case we must look at all the elements which are found in A obviously but should not be common to A and B both. In case there are any elements, we must remove them. The same applies for B minus A. I hope that's clear for all of you, my dear friends. Likewise, complement of a set. There's a lot of difference between complement and complement. Well, in simple words, COMPLI and COMPLE. In the sense of mathematics, we'll be sticking to the COMPLE meaning at least. That is, in the complement of a set is basically the set wherein it is U minus A. Let there be a set A. In that case, the complement of a set, which can be A dash, AC or A bar. This stands for the complement, which is equal to U minus A. All the elements which are found in the universal set but is not found in A. Let there be a set A which is a consonant. A complement would be all the vowels found in the English language, which is represented by the shaded region, that is, all is shaded except the area inside the set as represented by the Venn diagram. Last but not least, we have over here the important formulas which we learned together in this chapter, my friends. Fellow mathematicians, like I said, sets is found all across the universe. We have a lot to thank to sets, including a very great thank you to George Cantor for helping me out. In fact, in the textbook, the various other mathematicians who played a key role, and even that trigonometric series which created the world of sets today. Thank you and have a very setful day. Bye-bye.